Okay, so as I mentioned a moment ago, today we will be covering inverse functions. Okay. So in order to understand the definition of an inverse function, you need to be very comfortable and familiar with the notion or definition of just a function, right? So recall that a function is an assignment of elements from the domain set to exactly one element in a range set. So you should have that definition either written down near you just so you can see it, or just be very familiar with it. Okay, so with that, you can now define what it means for a function to be an inverse. So a function g is the inverse function of the function f if the following two things hold. Okay, so if you compose g with f, then this equals x for all x in the domain of f. And then two, if you compose f with g, then this also equals x. And this is for all x in the domain of g. Okay. So here is the formal definition of an inverse function. And it's a relatively simple concept. So just imagine, so we have some set here A, and then some set here B, and there's elements in here like that. Maybe I'll call this like little a, b, c, d. And then we have some elements over here, maybe 1, 2, 3, 4, 5. And just suppose we have some function f that maps a to b. So again, in order for this to be a function, each thing in the domain set needs to be mapped to exactly one element in the range set, or codomain. So maybe A gets into 2, B gets into 1, C gets into 3, and D gets into 4. Now the inverse function, which we will use the notation f superscript -1. So this is the notation for f inverse. F inverse is just going to undo or reverse the mapping that was given by f. It's going to take, so for example, if A was sent to 2, f inverse of 2 is going to send 2 back to where it came from, back to A. F inverse will send 4 back to D, it will send 3 back to C, it will send 1 back to B. Okay. So hopefully that's clear. So where did 1 go to? B. Okay. And then F inverse of 4 was D, and then F inverse of 3 was C. Now notice that this is a function, right? This satisfies the definition of being a function from B down to A. So f inverse goes from B to A, and it is a function. Everything here is mapped to exactly one thing over there. Now, there would have been a problem if f wasn't a special type of function. Like, for example, so if f behaved like this, then there would be a problem. Let me go ahead and give them labels now so you can see the problem explicitly. 2, 3, 4, 5. So if there was an inverse, it would tend 1 to B. So f inverse of 1 would be sent back to B. But then here at 2, what about f inverse of 2? It would be sent to both D and C. That's not a function. So here, in this case here, no inverse exists. Okay. And in a moment, we'll actually describe a characterization of the existence of inverses. It's actually fairly simple. You can maybe make it out just by looking at the picture that an inverse is only going to exist if the function is 1 to 1. Okay. But before we get to that theorem, let's just go ahead and find an inverse for a function. So let's say find the inverse of f of x equals to 2x cubed minus 1. Okay. Now, in maybe pre-calculus or algebra, sometime in your past, you might have been given a technique for calculating or finding the inverse where you switch x's and y's. I always find that somewhat contrived, maybe. I just like to go off the definition. And the definition says that if there is an inverse, then it better satisfy these properties. All right, so in particular, we know that f composed with g of x should equal x, right? That's just using the definition. This has to hold. I probably should have told you that in this problem, the inverse does exist. So, knowing that it exists, we're going to use the definition to find it. Okay, so if we know that this has to hold, then what is happening? We're just composing f of g, so we know that 2, and then we replace x by g. So we know 2 times g all cubed minus 1. We know that should equal x. Right? So then we just have to solve for g now, right? So add 1 to both sides. Divide by 2, and then take the cube root. You'll get that g of x is equal to the cube root of x plus 1 over 2. I use g, but you could, this is in the textbook, they'll probably write it back. That's the inverse. And you can verify it by just plugging this into that function, and you'll see that you get back x, right? If you put this in for x, this cubed, the cube root goes away, and then you'll have 2 times x plus 1 over 2. The 2's divide out, and then you'll have x plus 1 minus 1, you end up with x. So it will satisfy part 2 here of the definition. But then if you wanted to verify part 1, plug f into this function, and you'll get the same result. Okay. So now this is kind of the mechanics of computing it, but really in the back of your mind, you need to just be remembering that the inverse is kind of undoing what the original function did. And I know that it might seem like another arbitrary mathematical concept that professors just ask you to learn, but it is useful in a lot of applications. In particular, it's related to this notion of inverse problems. So where you know a function is generating some data, but you don't really, you have the outcome of the data, you want to know where it came from, right? So that's like finding the inverse of the function that generated the data. For example, the measures of gravity, the measures in gravity generated by the Earth give scientists a picture-ish of how dense the inside of the Earth is. Now, this is very oversimplified, but the measurements of gravity changes due to the Earth is like a function, and finding the inverse tells you what the original pieces were doing. Hopefully that makes sense, but that's like an example of why understanding inverses is important, because a lot of times we will have the data at hand, a function made it, and we want to know where it came from. So it's actually a lot more common than you think to ask yourself, what is the inverse of the function that made this data? Okay, we should probably talk about the graphs of these things. This theorem, I think, 5.6. So the graph of f contains the point AB if and only if the graph of the inverse, so the graph of f inverse, contains the point BA. And this is like, I should put in parentheses, assuming the inverse exists. So if the function has an inverse, then this biconditional statement must hold. F contains the point AB if and only if the graph of the inverse contains the point BA. Okay. So how would this be the case? Maybe give like a short argument for it. Suppose first, so whenever I write PF, it means proof. I'm not giving an argument why it's true. So suppose AB is a point on the graph of F. Okay, so if that point is on the graph of f, then it means that f evaluated at a is equal to b. So therefore, maybe f evaluated at a is equal to b. Okay. Now, assuming that the inverse exists, I'll write that out. Assuming that the inverse exists, we can just apply the definition and evaluate f inverse at both sides of that equation. So then f inverse of f of a equals f inverse of b, which means that f inverse of f of a is just a by definition. So that means that f inverse of b is equal to a. Hence, the point B, A is on the graph of f inverse. So that shows one direction of this if and only if this is a bidimensional statement, which means that this implies this and this implies that. So conversely, you would suppose that this point is on the graph of f inverse, and then to finish the proof, you would show that assuming that's on the graph of this implies that's on the graph of that. So I'm not going to finish the proof, but it's basically the same thing over again. So dot, and then dot. Now, what this says is that there exists some type of symmetry in the graphs of a function and its inverse. So, for example, let's just suppose that we have, well, this actually looks like natural log, okay? Okay. So, what is this point here? That point there is 1, 0, right? So if there is an inverse of natural log of x, then if the point 1, 0 is on the graph of that, then 0, 1 is on the graph of the inverse. So 0, 1 is like right there. Okay. And pretty much anything that you pick is going to be reflected across. So this would be, so if this was f of x, then this would be f inverse of x. And this is a consequence of this theorem saying that if that point's on the original graph, then that point is on the graph of the inverse. And this is the line y equals x. And in some of the homework that I'm going to suggest that you work on, you'll have a few problems where you look at the symmetries for a graph and the graph of its inverse. Okay. Next theorem.
So will there be instances where there is no inverse function?
Yes. So,
Okay.
so for example, so that function there would have no inverse. Why is
Oh,
that?
I see.
So thank you for speaking up, by the way. You're one of the first people to speak up. I like it. Please, all of you, try to interact a little bit more. It's kind of a dry just talking at a camera for an hour. So, so the graph of this is like this. So it's this parabola like that. Now, this function cannot have an inverse because, for example, here 2 gets sent to 4, right? But then also, -2 gets sent to 4, right? And the inverse is defined as a function, right? So if you look at the range of this function and you pick something in the range, for example, you pick 4, right? Where would f inverse send 4? Would it send it to 2 or would it send it to -2? It can't send it to both, so it wouldn't be a function. So this just cannot exist, which means that this function would not have an inverse. Which leads perfectly into our following theorem, next theorem.
Is it kind of relating to how you said to be a function, 1x can only have 1y?
Right, so the definition of being a function is that each x is sent to exactly 1y. So when looking at the inverse of this thing, if you try to send 4 back to where it came from, it gets sent to 2 different things, which makes it not a function. So yes, that's exactly why. And again, let's say it's very related to the theorem I'm about to write down. So 1 answers your questions, all of them. So a function f has an inverse if and only if, it's biconditional, f is 1 to 1. If and only if it's a bijection. Oh, no, not bijection, injection. So what does it mean to be 1 to 1? It means that x1 not equals to x2 implies f of x1 does not equal f of x2. So that's the definition of being 1 to 1. So the theorem states that a function has an inverse if and only if, meaning it's a characterization. The function better be 1 to 1 in order for it to have an inverse. And for example, here, x squared is not 1 to 1. You draw a horizontal line, it's going to intersect the graph of that function at 2 points, cannot be 1 to 1. And then part 2, like in addition to part 1, if f is strictly increasing, then f is 1 to 1. Okay. Hence, or maybe not hence, I'll say comma, which implies f has an inverse. So if your function is strictly increasing, that implies that you'll be 1 to 1, and all 1 to 1 functions have an inverse. So it's just another way of determining if a function has an inverse. Okay. I'm debating over whether or not I should prove this theorem. I'll talk you through part one, and I guess I'll write down part two maybe. So why would part one, like why would that be true? Well, if you assume that f has an inverse, then you would get that for each element in the range, there had to be exactly one element in the domain that was sent to it, based off of what I was arguing here. So that would imply that if it has an inverse, then it's 1-to-1. If you assume the function is 1-to-1, then you can explicitly construct an inverse by just sending each thing in the range back to the domain. So it's not really difficult to prove, it's just a little wordy to prove. For part two, if f is strictly increasing, then it's 1-to-1. I don't think that's hard to prove. Let's go ahead and see if we can figure it out. We'll prove from part two. So we assume it's strictly increasing and show that it's 1-to-1. There's not too many math majors in here. So I'm like debating over whether or not I want to talk about proving by contraposition or something like that. Yeah, I'll make a video of it separately. For those of you that are interested in seeing the formalism behind arguing this to be true.
That'll be on the YouTube channel, right?
Right, and I'm setting that up right now. It takes a while to render some of these videos and get them ready for YouTube. So bear with me, but maybe today the YouTube channel will be up. So.
Okay, sir. Thank you. Appreciate it.
Okay, so what else should we state? This is for later. Theorem 5.8. And this is really just a statement of, I guess, nice properties about inverses if they exist. So let f be a function with domain I. Okay, so there's several parts to this theorem. The first two kind of say the same thing, or no, well, sort of. So if f is a function with domain I, then if f is continuous on I, then assuming that the inverse exists, f inverse is also continuous on its domain. So does anyone remember what it means to be continuous, generally speaking? Like, you don't have to give me the formal definition, but just kind of vaguely describe what it means to be continuous.
There's like no gaps, no breaks in the graph or in the function, I mean.
Right. It's somewhat connected. If you try to draw the graph, it'll be connected. Formally, it means that so a function f is continuous at a point C if f is defined at C, the limit exists as x approaches C, and the limit of f as x approaches c is equal to the function evaluated at c. That's the formal definition. But altogether, what it means is that the function behaves okay. There's no jumps in it. It's not, there's no gaps. Okay, so part 2. Oh, I should probably elaborate, which is nice. A lot of functions that we deal with can be approximated by continuous functions. And if we're interested in their inverses, the nicer, the more well-behaved it is, closer to being continuous, the better. So this fact is nice. All right, so part 2. If f is increasing, or decreasing, so put that in parentheses. Then f inverse is also increasing. Or decreasing, respectively. Okay. Now, on your own, I really think that it would be nice for you to kind of justify this. Okay, like, kind of give me a reasoning, a formal argument, maybe why this would be true on your own. And just a heads up, whenever I do things like that, where I say like, maybe you should try this on your own, I circle it, I put a star by it. There's a chance it will appear sometime on an exam. It's like a bonus question or something like this. This, and again, all I'm asking is you think about why this is true and try to argue why this is true on your own. All right. So now finally, we're to the last theorem of this section. It's called Theorem 5.8 in the textbook, but I'm going to call it the inverse function theorem. That's how I know it. And whenever a theorem has a name, it typically means that it's important, very useful for something. So this one has a name, which implies importance. What does it say? So let f be a differentiable function. Okay, on the interval I. Okay, so if f has an inverse, say G, then G is also differentiable. Okay, differentiable at x provided one thing. So at any x with f prime of g of x not equal to 0. And the reason for that will become apparent when I write down the next formula. Moreover, g prime of x is equal to 1 over f prime of g of x. And again, we're assuming that f prime evaluated at g of x is non-zero. So this is the inverse function there. Now, why does it have a name? Why would I write it down? Why should you care about that thing? Well, a lot of times we can't explicitly compute the inverse. We can't, like in the first example that we had, we were able to write out the inverse explicitly. We just found it, right? But in a lot of cases, you can't do that. It's not so easy to find the inverse, even if it exists. And we're concerned about the rate of change in the inverse, right? Going back to like maybe understanding the dynamics of the Earth's crusts and mantle and the things inside based off of the measurements due to gravity that we observe, we would be interested at the rate of change of the stuff inside the Earth, right? And even if we can't find the explicit formula for the inverse function that's making the observations that we have, making the data that we have, even if we can't find that function, we can still evaluate the rate of change or the derivative, provided we have the sufficient amount of data, which is generating our function f. So that's why this would be useful. To say it a little bit more concretely, this function plays an important role in the study of partial differential equations, so PDEs. And PDEs are probably the most widely, PDEs are like the most applied math that you can probably do. It's study of equations where you solve them by solving for functions in terms of derivatives and partial derivatives, and it's a whole field, and it's an important theorem for that field. Now for us, we can use it to find derivatives of inverses without actually having to calculate the inverse. So for example, so let f of x equal to 1/4 of x cubed plus x minus 1 finds f inverse prime of 3. So we have a function and we're asked to find the derivative of the inverse. Okay. Now this function happens to be 1-to-1, so it has an inverse, and theoretically we could go through the steps to find the actual inverse, then take its derivative, then plug in 3 and get the answer. Or we can use the inverse function theorem to evaluate it immediately. How do we do that? Well, we need to find f prime, and that's basically it. So note that f prime of x is equal to 3/4 of x squared plus 1. So then what do we do here? So we know g prime of x is equal to 1 over F inverse, no, not F inverse, sorry. G prime of X, which is equal to this, by the way. I'll just use that notation instead. F inverse prime of X is equal to 1 over F of F prime of F inverse of X. So all I did was rewrite this in terms of F inverse instead of G, using that notation. Okay. So how can we do this? So we need to, now without computing the inverse, how do we plug into there, right? That seems kind of confusing, right? Should we calculate the inverse and then plug it in there, or is there another way around this? Let's see. I forget what I wrote down here. Yeah, we don't have to do much at all. We just need to figure out, so we need to figure out what values for X make 3 for F. So we need to know what X does that. And if you plug in, I think it's 2. Right, so 2 is going to be 1/4 times 2 cubed plus 2 minus 1. So this would be 8 over 4 plus 2 minus 1. Did I do that right? Yeah. So this would be 2 plus 2 minus 1. That's equal to 3. So I know that if f of 2 is equal to 3, then f inverse of 3 is equal to 2. So now I can plug in. So this is going to be equal to 1 over the derivative evaluated at f inverse of, I'll write it out, sorry, prime. And this is now f3. F inverse of 3 is 2. And f prime of 2 is what? 4. This is 1/4. And that's it. Okay. So notice that we didn't have to find out what the inverse was. That's the whole point of it. All we needed to know was what x got sent to 3, so we could know what f inverse of 3 was. It was 2. Once we found out it was 2, we just plug into the derivative, which was easy to find. And we have 1 over that, and that's the answer. Okay. So that will conclude the section on inverse functions.